Everybody. Hope we're all doing wonderfully. We're just going to jump right back into it in section 1.3. We're going to talk about some important types of functions, specifically exponential functions and logarithms. And there's an important relationship here that we want to make sure that we can properly identify. Okay. So the first thing I want to talk about is the concept of an inverse function. Okay. Not all functions are going to have inverse functions, but the idea is a reversal of the original function. And what I mean by a reversal is a reversal of the inputs and outputs. So, if f of x equals y, what we want is f inverse of y to equal back x. And we're going to use this notation right here, this -1. This is not a power in the traditional sense. This is telling us that we're finding an inverse. Okay? So, let's talk about what inverses are. I'm going to talk about them analytically. I'm going to talk about them using this manipulative, and then we're also going to talk about them using some graphs. So, maybe a good one to start. I like 3x plus 4. Here's f of x equals 3x plus 4. To find an inverse, here's what we have to do. Step 1, we rewrite, and by the way, I really should have started with 3x plus 4 equals y. Rewrite the equation with x and y reversed. So what is that going to look like? Well, if 3x plus 4 equals y, I'm going to write 3y plus 4 equals x. All good there. Step 2, solve for y. So let's see if we can't go through this. So I want to get this y by itself. I'll subtract 4 from both sides. We'll get 3y equals x minus 4. One more step, we'll divide both sides by 3. And we get a new function, x minus 4 over 3, or y equals x over 3 minus 4 over 3. Both of these are appropriate. I will say you're more likely to see a little bit this first one, this x minus 4 over 3. And the relationship that we want is perfectly captured. To kind of just bring you over here for a second, f of 2 is 3 times 2 plus 4 is 10. F inverse of 10 is 10 minus 4 divided by 3 is 6 over 3 is 2. And so you can see I have properly found the inverse. Now, as we get a little bit further, these are going to become a little bit harder, right? That's what normally happens. But even though they're harder, we can still find them. Let's look at something like, grabbing my ink, let's look at something like f of x equals the square root of x minus 9. Can we come up with an inverse? So once again, we start off y equals the square root of x minus 9. And you know what? Just for fun, let's make it a cube root. I think that's fun. So, step 1, we're going to rewrite the x and the y. Sorry about that. Okay. And now we're going to try and solve for y. So, how do we undo a cube root? We'll cube it. This is x cubed equals y minus 9. How do we undo a minus 9? We're going to add 9 to both sides. I like to write y on the left-hand side. We get y equals x cubed plus 9. Now, one more step. Specifically, we want to specify the inverse of this original function. Let me go grab it. And you can see a lot of the same structure. Just to kind of visually indicate some things, we have a -9 going to a +9. We have a cube root going to a cubing. Now it's very important. This negative sign is underneath this cube root, but this positive sign, this addition sign, is not underneath this power. Okay? And there's rules for this, and you can kind of go a little bit further if you're interested. This is really all we'll need right now. One thing I do want to point out is there's a very special relationship between, once again pulling up some Desmos, a function and its inverse. So let's talk about some functions and their inverse. The one that we just looked at, this was 3x plus 4. And what we got as an inverse was x minus 4 divided by 3. Okay? So we have a red function and we have a blue inverse. Now, something very important is that you could imagine, I'm just going to color, this blue line is a reflection of the red line, and it's a reflection about this dotted line. Okay? And that turns out is the graphical representation of an inverse, is that you have this symmetry. And it works for everything. So for example, we just got, what was it? X minus 9. Cube root is the same as 1/3. And we also got x cubed plus 9. And let's zoom out so we can see that. You can see that this red curve, you could almost kind of flip these together over each other like a book. You could reflect about this y equals x line. So that's the graphical representations. But how do we end up finding inverses? It turns out most of what we do is we're doing something like this, where we are interchanging the role of x and y and then eventually trying to solve for something. Now, some things don't have perfect inverses. I actually want to, real quick, I want to give you an example. This is something that's going to happen a lot, is if we take a look at, let's say, f of x equals x squared. You know, there's really nothing fancy here. You might, okay, what's the opposite? What's the, inverse of a square? Maybe you think it's the square root. Okay? Turns out, more complicated. And for reasons, let's go to the graph. So here's x squared. And then down here, we'll do the square root. Whoops, that's all caps. Square root of x. Now, if we just look right here, they look pretty good. This seems like a reflection of that one. Yes, they have that cool intersection point. But as we scroll out, where is this part over here? Well, the problem is that if we were to include this sort of blue line in the parabola, we kind of rotated it, the thing that's over here would get mapped down here, which would cause this square root to no longer be a function. So the important thing to note is only an inverse on 0 to infinity. The negative pieces of this we can't get. For example, f of 7 is 49. And that also means that f inverse of 49 is 7. And that is true and true. But f of -1 is +1, which does not work because f inverse of 1 is not -1. It actually only tells us the positive. Okay? Now, you can, if you're okay without a function, you can say f inverse of x is the positive or negative square root of x, where sometimes you take the positive one, you take the negative. But unfortunately, that stops being a function. We find it a little bit easier to restrict the domain than to have something that is not a function. So I just want you to be aware of that. Now, most of the things that we're going to look at have functions, even if we have to put them as functions only on certain domains, and maybe the inverse of themselves go a little bit crazy on the domain. But the important thing is, if a function is 1 to 1, it has an inverse. Now, what does it mean to be 1 to 1? 1 to 1. Each input has a unique output. So let's go back to our first, we were talking about some sets. So here's A, set B, and here's F is going to take us from A to B. And let's say we have 1, 2, 3, and we have A, B, C. So real easy, 1 goes to A, 2 goes to B, and 3 goes to C. All well and good. This is a function. And it's 1, 2, 1. Okay? Now, let's add in another element over here. D. And if we make 2 go to D, I want to point out we are no longer a function because one of our inputs is going to 2 outputs. Okay? Let's get rid of that. Let's get rid of D. But what if we instead added something over here? 4 goes to C. This is still a function, but it's no longer 1 to 1. Each input does not have a unique output. Specifically, 4 and 3 are sharing their outputs. There is not an inverse function, because you could think about it. Let's rewrite it going from B to A. This would be the function f inverse. We have A, B, C. We have 1, 2, 3, and 4. So we have, if it's an inverse, A should go back to 1. B should go back to 2. And now C is going to both 3 and 4. What we want is if you are 1 to 1, it implies your inverse is also a function. We're avoiding that repetition. Okay? So, another way of saying 1 to 1 is just saying, is the inverse a function? Does each input have a unique output so that if we reversed it, every new unique input would have another unique output? Okay. Now, lots of things have inverses, and they come in these, pretty standard pairs. We just saw x cubed and 3x. We have multiplication and division, addition, and subtraction. But there's a really important inverse that has to do with exponential functions and logarithmic functions. So, exponential functions are functions where the independent variable is up in the exponent. Lots of students get these confused with polynomial, where we have an independent variable raised to a known power. Now we have a known base raised to an independent variable power. Okay? It turns out undoing these exponential functions are a little bit tricky. That's where the logarithm comes in. So, let's talk about exactly what these pieces tell us. Sorry, I want to get rid of that. So, when we write something like 3 to the x, that means we're going to multiply 3 times 3 times 3 times 3 times 3 x number of times. And we can choose x to be a fraction. We can choose x to be lots of different things. And that's where your, innate understanding of these terms is a little bit tricky. But it turns out it's so useful, we just want to power through. We want to make sure that we can still understand them. Okay? So, something that you might recognize real easy, 3 to the x equals 9. Can we solve something like this? Well, a lot of you are saying, oh, well, x clearly equals 2. And you just know that 3 squared is 9. Okay? What about 3x equals 9.5? It's not 2. It's maybe a little bit more than 2. What we want to do is we want to introduce something that we know for sure undoes our exponentials. And that's actually where logarithms come in handy. Here's the important thing. Logarithms. They undo exponentials. Okay? That's all you have to think about them. Now, over this class, as we start to use them a little bit more, we'll figure out that they're useful in their own right. But that's really their intention, is that they undo an exponential. So you can take any logarithmic statement, let's say b to some power p, and we'll set that equal to n. If this statement is true, we can also write that the logarithm of base b of that number m is p. And the two most important words we should write are the base stays the base, and we are also want to make sure that a logarithm is equal to a power. So, as some examples, I'll go over here and I'll write some exponentials that we hopefully know are 2. For example, 2 to the 3 equals 8. Hopefully that's one that you're familiar with. Can I rewrite that? Well, I know what the base is, so that's going to tell me that the log base 2. I know what the power is, and I know that's going to equal 3. And then what's kind of left over is that m term, the 8. So if it's true that 2 cubed is 8, it must also be true that the logarithm base 2 of 8 is 3. 3 to the negative 2 is 1 over 9. I can rewrite that. The log base 3 of 1 over 9 is negative 2. Making sure that I'm matching up the base and the power. 10 to the 5 is 10,000. Log 10,000 is 5. Notice, when my base is 10, I actually don't write anything. It's called the common log, to kind of just come up here. The common log, log of m, is the log base 10 of m. Our number system is base 10, so it makes sense that the understood logarithm would be base 10. There's another very important logarithm called the natural logarithm, which is ln, which is just the logarithm base e. Now, what is e? E is sometimes referred to as the natural number, and it's something that shows up in a lot of different places. We will actually more explicitly define e. It's something that you can do in a later calculus class, which is, of course, very interesting. But the important thing is we want to make sure that we recognize these two logs as special. Every other log, log base 3, log base 2, log base pi squared on 6, those all have to be written. The only two that you don't have to write a subscript on is the common log, which is base 10, log, and the natural log, which is base e, ln. Now, why do we care about logs? Well, logs have some interesting properties that are actually going to help us solve some things. For example, going back to my original problem, we said that 3 to the x equals 9 is solved when x equals 2. Wow, that's a horrible 2. But we wanted to solve 3 to the x equals 9.5. Now, how can we solve this one a little bit better? Well, what if instead of just saying we know it's 2, what if we converted it to its logarithmic form? Log base 3 of 9 equals x. And this wonderful thing right here is something we can plug into our calculator. And if you do that, you will find that you get x equals 2. Now, that's something that we could have known. What's even better is if we do the same trick over here, we'll find that the log base 3 of 9.5 is x. That's the power that's going to solve that. And again, this is something we can plug into a calculator. In fact, let's go ahead and do that right now. Oh, sorry, I was searching for a TI-84, but I realize what I'm going to have to do instead is just go back to Desmos. Now, please feel free to use your TI-84s. And if you have questions about them specifically, that's something I'd love for you to reach out to me. But if we type in the log base 3 of 9, we get the answer is 2. And what is the log base 3 of 9.5? We get a pretty garbage answer, but the important thing is if I take 3 to the power 2.0492141056.7, I get awfully close to 9.5. Is it exact? No, because this number's digits go on forever, and I don't really have time to deal with that. But we can get very, very good approximations. What is the actual value is, well, it's just the log base 3 of 9.5. So that's kind of all we have there. So that's the first use case for utilizing logarithms. Why logs? Reason 1. Solve exponentials. Now, what are some other reasons why we use logarithms? They have nice properties. And let's take a look at an example of that. If you have something, and I want to set this up as an exponential case versus a log case. You might be aware that if you take, and I'll use 10 as an example, 10 squared times 10 cubed, you have this ability to add these two numbers together and find that it's 10 to the 5. Turns out that property exists in logarithms, but it's a little bit opposite. Remember, exponentials and logarithms are inverses. They undo each other. So, the logarithm base 10 of 3 plus the logarithm base 10 of 2 turns out to be the logarithm base 10 of 6. In the exponential world, we had multiplication becoming addition inside the exponential, outside multiplication inside addition. In the logarithm case, we have outside addition becoming inside addition. In fact, I don't even want to write this as 6. I want to write it as 3 times 2, which turns out is 6. Similarly, we have 10 to the 8 divided by 10 to the 5 will be 10 to the 8 minus 5. It's 10 to the 3. We can rewrite this case as a logarithm of 8 minus the logarithm of, let's go 2, is going to be the logarithm of 8 divided by 2. Outside division, inside subtraction, becoming outside subtraction, inside division. Last but not least, this is the most important rule for logarithms. This is the one you're going to use the worst, sometimes called the power rule, which says that if we take something like 10 to the 8 squared, well, that's going to be 10 to the 8 times 2, or just 10 to the 16. This one is a lot trickier in logarithms. The logarithm of 8 squared, we can actually pull this 2 right into the front and write 2 times the logarithm of 8. We can pull out exponents from inside logarithms as multiplication outside a logarithm. So, what if the logarithm of x squared equals 3.2? Well, that 2 can get pulled out to the front. 2 times the logarithm of x is going to equal 3.2. We can divide both sides by that 2. Sorry that it's becoming curved. I physically turned my body when I looked at this left-hand part of my screen. We find that log of x is 3.2 divided by 2. Or, let's just write that as 1.6. Look, I solved the logarithm by just utilizing its powers. Okay? We're going to use properties of these logarithms several different times in whatever use case we need. And it's just something that as you get through them more and more, you start to get a lot more practice on them. Okay? Let's take a look at an example. And by take a look, I'm actually just going to pull it up on my second screen. Okay, let's try to solve the logarithmic equation log base x of 3 equals 1/2. So the question is, what is the value of x? That's the log of that base of the number 3 gives you 1/2. Well, this is an excellent chance for a rewrite, and that's usually what we end up doing. Remember, the base stays the base. A logarithm equals a power. A base to the 1/2 equals 3. Now, what does it mean to raise something to the 1/2? It is the bth root of x to the a. So this is saying the square root of x is 3. Or, I think we get x is 9. I'm just checking it from your homework. I did it! That's good. I'm glad I'm able to do your homework. Let's take a look at another log type question. Let's try to solve log base, or let's do some ln. ln of x equals 2.7. Remember, ln is log base e. There's our base. There's our power. Let's rewrite e to the 2.7 equals x. Now, what is e to the 2.7? Again, this is something you can find on a calculator. And we'll use whatever decimal precision we are asked. The important thing is that by rewriting exponentials as logarithms and logarithms and exponentials, we can get some interesting work. As a final one, let's take a look at the log base 2 of x plus the log base 2 of x minus 3 equals, I don't know, let's just say 16. Okay, first things first. We have two logarithms. We would like to rewrite it, but unfortunately, when we have two logarithms, we need to combine. So the rule is, again, there's an association between addition and multiplication, division and subtraction. So this addition actually can be rewritten as the log base 2 of x times x minus 3. And that's one logarithm equaling 16. Now, how do we solve that? We'll say 2. Oh, goodness. I made this one up. I realize now that this is going to be really, 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 really bad. I want to write this real number as 2. Because we have a base, we have a power. 2 squared equals x times x minus 3. Or 4 equals x times x minus 3. Now please note, we cannot, I'm going to write this in, I'm going to go red, but specifically I'm going to go a different brush because I want you to make sure that this is bad. Do not do. You cannot say that 4 equals x and 4 equals x minus 3. You cannot do that. In fact, I don't even like looking at it as a... I'm just going to undo my way until we get out of here. We only did that in a previous lecture because of the zero product principle. There are only two numbers that multiply to equal 0. One of them has to be 0. There are tons of numbers that multiply to equal 4. Okay? Not any of them have to be 4 individually. If we really want to solve this, we're actually going to distribute out x squared minus 3x equals 4. We will, more than likely we are a big fan of factoring. And just to give you kind of a taste, I think we can do x plus 1 times x minus 4. Now this is the zero product principle. We can say that x plus 1 equals 0, or x minus 4 equals 0, giving us that x equals negative 1 and x equals 4. That's a little advanced. That's using some factoring that we haven't technically gotten to. Hopefully you got to it in your college algebra. I actually think 1.4, let me go ahead and take a look at the assignment manager. We will talk a little bit more about factoring when we get into limits on section 2, but this is just a good sort of idea. Hopefully these terms, and again, I want to stress this as we go through these, there's lots of resources available to you. I hope that you're watching these videos, maybe on 2x speed, just saying. Hopefully you're using the built-in help file to solve. At any time that you have these questions, these are the things that I offer all students. If you ever want to talk to me in a Zoom call, you ever want to be live talking to me, or if you have some homework questions that you want to send to me, and you want to say, hey, I would like to spend some more time on these specific ones, please let me know those things. I would really, really love to get the chance to talk with those about you. As a brief, kind of end of this section, I want to talk about two things. They're a little outdated. Well, the first one's outdated, but it's still somewhat important. It's called the change of base formula. If you are going to evaluate the log base b of some number m, you probably have found ways to do this on your calculator. Turns out it might be faster to represent it as this fraction, where you can just take the logarithm base e of m and divide by b. So for example, the logarithm base 8 of 64 is the natural log of 64 divided by the natural log of 8. Does that help you? No, not really, but there are some older texts that you might be reading, and they might be doing a lot of this, so I just like to shout it out. And the second one that I want to talk about is, there is another way of writing this. So sometimes we might say 3x equals 9.5. And we want to solve this. Now, the way that I solved it was, I would say something like, let's rewrite it, right? Some people might instead take a logarithm base 3 of both sides. And they might write something like this. Now, it's the exact same thing if you actually did the rewrite, but it's more in line with, a lot of the times when we're solving these things, we like to do something on both sides. The square root of x equals 5. We're going to square both sides. 3x equals 9. Oh, I guess I don't need the parentheses. We're going to divide both sides. This is just more in line with doing something on both sides. So, you can take a logarithm on both sides, and the log base 3 and 3 cancel. Also, if you have a logarithm, you can still do something to both sides. It feels less satisfying, but you actually take e to the power of both sides. Sorry, not e. Take the base to the power of both sides. In this case, let's undo some of those. In that case, 3 and 3, and you actually can cancel get that both sides. So again, if you did the rewrite version, you write the same things. But also, I will say, doing something on both sides is just more algebraic, it feels. And so you might find yourself doing that a little bit more. All right, this is another video. I hope you guys found it entertaining. I hope you guys found some use out of it. Again, please, I am still your instructor. Email me, tchisholm1@uca.edu. I'd be more than happy to answer any questions that you have. And I wish you all the best.